This is for midterm 2A, spring 2017, number 3. A thin copper wire is oscillating on a conducting loop such that x of t equals x naught plus alpha sine omega t in a time-varying magnetic field given by b of t equals b naught minus beta t squared into the page as shown in the figure. What is the induced current on the loop? What is the direction of this induced current at t equals 0 plus? The total equivalent resistance of the loop and wire is R. So first we're going to look at the flux, because the flux will help us find VMF, which will then help us find the induced current, and then we'll use Lenz's law to look at the direction of the induced current. So the flux is given by the integral of B dot dA, and B is always going to be into the page as shown and as stated in the problem, but dA is a function of dx, and dA you can find by multiplying L and dx together, and dx is just the small change in distance of the thin copper wire as it moves from position 0 to x. And when you solve that, that gives BLX, and so taking the flux and finding the derivative and multiplying by -1, we can solve for VEMF. But there are two things that are changing in the flux equation, and that's the B field and the distance, because they're both functions of time. So we're going to have to do the product rule. So we're going to have B times dx over dt plus x times dB over dt, and then multiply that by -L because L is constant. So taking the derivative of dx over dt gives us alpha omega cosine omega t, and taking the derivative dB over dt gives us -2 beta t. And it should say -2x beta t, not +2x beta t. That's a mistake. So the next line gives us -L, and then multiplied by the quantity. And so b naught minus beta t squared is just b in the previous line, and then times the derivative of dx over dt, which is alpha omega cosine omega t, and then again this should be minus 2 times x of t, which is x naught plus alpha sine omega t beta t, and then -2 beta t was our dB over dt. And so we can find our induced current by taking VEMF over R, and we're only going to look at the magnitude because Lenz's law will help us find the direction. So again, the current is just VEMF over R. So we're going to use Lenz's law to find the induced current, the direction. So the area is increasing, which means the flux is increasing. And we know that the area is increasing because it's x naught plus alpha sine omega t, and when t is 0 plus, then x of t increases. And we're going to induce a B field to oppose the change in flux. So originally the B field is into the page and giving a clockwise current, but to oppose the change in flux, we're going to induce a B field in the opposite direction, which is going to give us a counterclockwise current. We know that the area and the B field are a function of time, and so they're both changing. We know that the change in area is going to increase the flux, and it's going to cause our induced current to travel in a counterclockwise direction. However, we didn't talk about the change in the B field. The B field is decreasing with a small change in T, and so a decreasing magnetic field means that we're going to want to induce a magnetic field in the same direction to make up for that loss, to oppose the change in flux. And so inducing a magnetic field in the same direction as the original magnetic field, which is into the page, gives us a clockwise direction using the right-hand rule. But we're able to disregard the effect of the induced current of the magnetic field, because if we look at our current equation, we see that b times dx over dt is a function of cosine, while x times db over dt is a function of sine. And so when we have a small value of t, such as 0 plus, the sine term is going to disappear, and we're only going to be left with the first term, which is L times b dot dx over dt. And so we see that only the change in distance is affecting the direction of the induced current at small t. And so our induced current when t equals 0 plus is going to be in the counterclockwise direction because of the change in area, which is due to the change in distance.